Hello everyone, welcome back to the next video. I'd like to remind everyone that the best way to study using these problems is to try them honestly yourself before watching these answers. So, let's just get to it. The accelerating force of wind on a small 200 kilogram sailboat is 707 newtons northeast. If the drag of the keel, whatever that is 500 newtons acting west, what is the acceleration of the boat? So this is another vector problem. So here's my boat. Boats are triangles. Northeast, we've got 707 newtons. Okay? Now, it says exactly northeast, and I take that to mean that this is exactly between north and east, so I'm going to say it's 45 degrees. Now, if the drag force in the keel is 50 newtons west, or 500 newtons west, then what is the acceleration of the boat? So we have to do two things. We have to figure out what the resultant force is, because that will be equal to our net force. And then we can take net force equals ma, and we can solve for a. So we've got 700 newtons going this way, 500 newtons going this way. And this is very similar to a problem we had on one of the earlier documents, where we can break up this force at an angle into two smaller vectors, and then we can add them up from there. So that's exactly what I'm going to do in this extra piece of paper. So triangle here, 500, 707 with a 45 degree angle. So let's look at this 707. We've got this one going this way and this one going this way. And so since it's 45, both sides of this triangle should be equal, okay, because this is also 45 degrees up here. So whatever one side is, both sides are going to be the same. So 707 sine of 30, you could use cosine, it should be the same number, 353.5 newtons. And just checking, oh, I did sine of 30. That was wrong, sine of 45. So sine of 45 gives us everything short of 500. Yeah, so 500 on both sides, okay? So we have this triangle, 500 on both sides, and this actually makes it kind of easy, because now let's put them together, doing them one at a time. So we've got this 500 Newton thing going west. Then we've got 500 newtons from the big force going east. And then we've got 500 newtons going north. And so the end result of all of that is just the 500 newtons going north, because the 500 newtons east and the 500 newtons west are going to cancel each other out. So 500 newtons north is going to be the net force, and now we can take that back to our problem. So if it's literally just 500 going north, then we can take 500 and put it in for our net force. So 500 newtons divided by the mass, which was 200, will give us the acceleration. So 500 divided by 200 should give us 2.5 degrees, 2.5 meters per second squared, which is an option, and it says it's due north, which we completely agreed with. Should be going straight north. All right, a 5,000 Newton weight is held suspended in equilibrium by two cables. Cable 1 applies a horizontal force to the right of the object with tension T1. Okay. Cable 2 applies a force upward to the left at an angle of 37 degrees to the negative x. So basically, if this is the negative x axis, 37 degrees is between T2 and that axis. What is the tension in T1? Now, this seems like a hard problem. You have to remember that the weight is involved, 5,000 newtons. Now, which one of these two forces is actually going to be holding up the weight? Well, it can't be T1 because that's completely horizontal. X direction stuff cannot affect Y direction stuff. T2 has two components, one that goes in the Y direction, one that goes in the X direction. So therefore, this part of T2 has to be 5,000 newtons, because it's the only vertical force that could stop the object from falling. It's the only thing that can cancel out gravity, which means that if this cancels out this and nothing's moving, that means the T2x component here has to be equal to T1. And so basically this comes down to, once again, a triangle, and a pretty easy one. This is T2, but we don't even need to know what T2 is, because we know that this side is 5,000. We know that this angle is 37. And we're solving for T2x because, like I said before, T2x and T1 should balance out. So whatever T2x is, this should be equal to T1. So I got the opposite side is 5,000. I have the angle, and I just want to solve for the adjacent side. That means tangent's going to be the quickest and most efficient way to do it. If you wanted to solve for other things and then take the long way around and still get the right answer, perfectly fine, but tangent's going to be the quickest way to do this. So plugging in my numbers, solving for the adjacent side, we've got 5,000 multiplied, I think it's 5,000 divided by tangent of 37 degrees. Yeah, like that. So 5,000 divided by tangent of 37 degrees gives me 6,635 newtons. I'm going to check the answers. 6,640, that's option B. All right, moving on. The box is to be moved across a level surface. A force of magnitude 200 newtons may be applied at an angle of 30 degrees below the horizontal to push the box, or at an angle of 30 degrees above the horizontal to push the box. Either application is sufficient to overcome friction and move the box. Which application will cause the greater acceleration? You guys in class, I believe, were able to do this pretty nicely. So two boxes being pushed along, one's being pushed like this, and one's being pushed like this. Now this goes back to a problem we had earlier, where in this case you're going to have a larger normal force because it's pushing downward into the table, which the normal force will have to fight against. This one you're going to have a much smaller normal force. Now because force of friction is equal to mu times normal force, a larger normal force means a larger force of friction that's going to slow it down. So this one's got a little force of friction, and this one has a really big force of friction. All right, so this one's going to be slowed down and therefore not accelerate as much. So this one with the upward force is going to have the larger acceleration. So which application will cause the box to have greater acceleration? The one above the horizontal. So that's B. Now, 3 different mass projectiles are launched from the top of a building, each at different angles of elevation. Each particle has the same initial kinetic energy. Which particle has the greatest kinetic energy just as it impacts with the ground? Okay, so this is very interesting. And you have to remember the equations for kinetic energy and what it's going to be. So everything starts with the same velocity, right? So 3 projectiles are launched from the top of the building, each with different angles of elevation. Each particle has the same initial kinetic energy. So we start with the same amount of kinetic energy for all of them. Which particle has the greatest kinetic energy just as it impacts the ground? Well, we can kind of forget about the kinetic energy that it starts with because that's all the same. And so it'll still have that energy on the ground. What I'm interested in is the potential energy. Now, each of these objects are going to start with a different amount of potential energy, even though they all start at the same height. They have the same height, but all of them have different masses. That's an important detail to remember because if you have a larger mass, you're going to have a larger potential energy. So objects are going to fall from the top of the building down to the ground. It doesn't matter what direction they're shooting at. Angles and directions don't really matter when it comes to energy. So it's going to fall to the ground, and all of the kinetic energy they have will still be there. The difference is all of the potential energy they start with is going to be changed into more kinetic energy at the end. So who started with more potential energy is going to have more kinetic energy at the end. So whichever one has the largest M, whichever one has the largest mass at the beginning, is going to have the most kinetic energy at the end. So the one with the highest mass, answer B. that's it for this video. I'll see you guys in the next one.